So we're going to go ahead and take a look at weak bases. So much like the equilibrium constant for acids or other equilibrium expressions, we utilize K sub B to represent the equilibrium constant for the dissociation of a specific base. If we look at the equilibrium expression here, notice it's directly related to this base picking up a proton and giving this subsequent conjugate acid and conjugate base. Okay, notice we have our two products, the concentration of our two products, the conjugate acid and conjugate base, and the base that we originally started with in the bottom of the equilibrium expression. As with the equilibrium expression for acids, we obviously exclude anything that is a pure solid or pure liquid from the equilibrium expression overall. So here's a list of some common weak bases, ammonia being probably one of the most common. However, we have several different amine types that show up, and they all have specific Kb values associated with them. As you can see, since these are weak bases, they have relatively small Kb constants. So Kb is that ionization constant for specific bases. So if we look at a specific example as opposed to the generic one we just viewed, we have ammonia reacting with H2O to give us ammonium ion and hydroxide ion in solution, and we subsequently get this Kb. Now understand that the higher the Kb value, just like any other equilibrium constant, the higher the base strength. So basically, the larger your equilibrium constant, the farther to the right the reaction goes, and subsequently the more OH minus you put into solution for that specific base. Okay, so when we're solving Kb problems for weak bases, we're going to solve them exactly like the weak acid problems, except instead of solving for H+, we're going to be solving for hydroxide ions. And once we solve for the hydroxide ions, obviously POH is what we'll have to solve for first before progressing into pH. Okay, so as long as you're familiar with the fact that you're dealing with a base, you should be able to be comfortable with identifying that you need to solve for hydroxide and subsequently make the appropriate steps to get into POH and pH. Okay, so they've asked us here to calculate the concentration of hydroxide in a 0.15 molar solution of ammonia. Okay, we know that ammonia is a weak base. Okay, so we know that in solution we're going to be producing the following. Okay, and we're going to set up that ice table just like we normally would. Okay, and we know that our initial concentration of NH3 is 0.15 molar. Okay, and our initial concentrations of our ammonium and our hydroxide ions are 0. Okay, obviously our concentration of NH3 is going to be decreasing. Okay, and the concentration of our conjugate acid and conjugate base are going to be increasing. All right. And we subsequently get the following values at equilibrium. Okay, and just like with weak acids, we set up our equilibrium expression, but in this case we're going to set it up with respect to the ionization products of the base. Okay, so the ammonium and the hydroxide ion. Okay, and of course our original concentration of NH3. Notice I've left out the H2O from the expression here because it's not going to be a factor in our equilibrium expression. Okay, so then like normal, we know our Kb value, so 1.8 times 10 to the negative fifth. Okay, that's going to be equal to x squared over 0.15 minus x. Okay, and we're subsequently obviously going to work on solving for our x value. Okay, so in this case what I'm going to do is I'm going to assume that x is going to be very small because my Kb is very small. So what I'm actually going to end up with in terms of my equilibrium expression is going to be as follows. Okay, I'm going to drop off that x value that we see here. Okay, and that's going to subsequently give us x squared being equal to 2.7 times 10 to the negative sixth. Okay, and in order to solve for x, I'm going to take the square root of both sides here. Okay, and x is subsequently going to be equal to 1.6 times 10 to the negative third. Okay, and if I check this value versus my original concentration, I'm less than 5% in terms of size, so I can make this assumption and move on. Okay, so now that I've solved for x, that means that according to equilibrium, I technically know the concentration of my hydroxide ion. Okay, and I could subsequently take this value and solve for a slew of other things. Now, let's say they wanted me to solve for pH. Okay, remember that I have solved for OH concentration. So when I take the negative log of the OH minus, that's actually going to give me POH. Okay, and then in order to go from POH to pH, I'm going to use this equation, okay, to get the appropriate value. So this is one of the ways that we could progress through this type of problem, but as you can see, it's very similar to what you would do with a weak acid problem. The only difference is in these situations, you're actually going to be utilizing the calculation to solve for your hydroxide ion concentration. So there's two categories of weak bases. The first category is a set of neutral substances that have an atom with a non-bonding pair. Okay, and so basically these can usually be categorized as amines. Okay, and basically what you end up with is something okay, like the following. Okay, so basically you have these two lone pairs on that nitrogen, and those can be a location where protons can be accepted, right? So the R values here can be any hydrocarbon, so you know, CH3 or whatever, and of course ammonia is, you know, the primary example of a weak base that we've been looking at it so far. Okay, the other option is the anions of weak acids. Okay. So the anions of weak acids are going to be substances that can basically behave as bases in solution. Okay, so if we consider ClO minus, which is actually the conjugate base of the weak acid hypochlorous acid. Okay, so when it disassociates, we end up with this conjugate base and a little bit of acid. Okay, so conjugate bases of, or the anions produced, or the conjugate bases of weak acids, actually can behave as weak bases. So when we have something like this, okay, so sodium hypochlorite, okay, this is going to disassociate into water as the following. Okay, now we just indicated that this can behave as a base in water. So what's actually going to happen is the anion is going to interact with water, okay, to produce the following. Okay, and as you can see, we actually have hydroxide ions in solution, which subsequently would increase the pH of any solution that actually contains the sodium hypochlorite salt in solution. So we do need to keep in mind those conjugate bases that are produced from weak acids, and basically the simple fact that they are able to behave as weak bases in solution and can subsequently affect your pH. So there's a quantitative relationship between conjugate pairs. So if we go ahead and we look at the example here, we're looking at the relationship between HA and its conjugate base A minus. Okay, so we're trying to find a relationship between these two species. Okay, so basically if we look at the dissociation process of the acid HA and basically the ionization process associated with the conjugate base of HA, okay, we sum those two equations together, we end up with this expression here. Obviously this expression here is directly related to our equilibrium expression for the autoionization of water. Okay, so that leads us to this relationship here. Okay, so the Ka and the Kb of conjugate pairs, when you multiply those values together, you will get Kw. Okay, and what's neat about this is that we can utilize this to figure out our Ka or Kb of related conjugate base pairs. And we can see some of these data points in data table seen here. Okay, so if we look at various acids and their conjugate base pairs, we can look and see the relationships that are produced. So HSO4 minus, okay, its Ka value as follows. Okay, the SO4 2 minus, the sulfate ion that's produced, has a Kb value of the following. Okay, and if we use the relationship between these two conjugates, okay, we would be able to solve for, you know, one or the other. So if I was given Kb, I could plug Kb in, I could plug in Kw, manipulate this equation, solve for Ka, and find my Ka value for the acid base in this acid in this acid base pair. Now, sometimes Ka and Kb are expressed as pKa and pKb. And the reason why this is the case is because sometimes it's easier just to relate numbers that are, you know, not really large, that don't contain really large exponents or really small exponents. And basically, this manipulation allows it to be smaller number of values that we can deal with a little bit more easily. Okay, so how do we calculate pKa and pKb? Basically, we just take the negative log of our Ka or the negative log of our Kb, respectively. And what's neat about our pKa's is that they are related similarly to how pH and pOH are related. So pKa plus pKb is going to equal 14 at 25 degrees C. Okay, so this relationship obviously can lead to you being able to solve for, you know, either your Ka or your Kb through an additional set of manipulations. All right, so let's go ahead and let's calculate our Kb for the fluoride ion here. Okay, so HF is the acid. Okay, so the conjugate base is F minus, or the fluoride ion. Okay, they've given us the Ka of our HF being 6.8 times 10 to the negative fourth. Okay, and they want us to calculate Kb. Okay, and you know, as we've been told, the relationship between Ka and Kb for conjugate acid-base pairs is as follows. Okay, so if I want to know Kb, I need to manipulate the equation. So Kb is going to be equal to Kw divided by Ka. Okay, and if we go ahead and plug that in, 1.0 times 10 to the negative 14 divided by 6.8 times 10 to the negative 4. Okay, that's going to give us 1.5 times 10 to the negative 11th, okay, as our value for Kb for our fluoride ion. Now, guys, understand that these Ka and Kb calculations must be for conjugate acid-base pairs. So basically, they need to be related. So, you know, please don't just use this randomly.